This video is going to be an introduction of the aircraft systems related to the Cessna 414 by FlySimWare for Microsoft Flight Simulator. This airplane can carry 7 passengers and only requires 1 pilot. The maximum takeoff weight is 7,105 pounds. The maximum fuel capacity is 1,236 pounds or 206 gallons, giving the aircraft a range of just over 1,000 nautical miles. Normal cruise speed is 230 knots. The surface ceiling is 30,000 feet, and the aircraft is powered by 2 Continental TSIO-550As. And why is the engine type brought up? Well, that's because the TSIO actually means something, and part of that designation actually makes this airplane what it is in performance, and that part is the TS, or turbo supercharged. And that turbocharger does increase the aircraft performance quite a bit, but the turbocharger also has other functions on this airplane, which we'll get into later. I means that the engine is fuel injected. O means the cylinders are horizontally opposed versus in a V shape that you would have in a car. And the L simply means the engine is liquid cooled. The 550 generally means the cubic inch displacement of that engine. The airplane itself is the Cessna 414A. The W is added because it has winglets, which is part of the Ram conversion. Jumping inside the airplane, the first thing to cover, the Annunciator Panel. There are 4 different colors of lights: red, amber, white, and green. Believe it or not, each color of light has a meaning. For example, if a red annunciator appears, that means an immediate corrective action needs to happen. An amber annunciator means corrective action needs to be taken, but it doesn't need to be immediate, but if you leave it alone, chances are something bad will happen. Green and white messages means that a normal or safe operation is occurring. For example, you turned on the windshield heat, and that green message shows up showing that you did something. A white message is normally a status message that just shows that something happened, but it's not dangerous. In this airplane, the only white message that means something is courtesy light, and that means that you did something. You turned on the courtesy light, and there's 2 switches, and we'll cover both of those in this video. And don't worry, there will be video after this image. They're not all just screenshots throughout the video. Starting at the top, the low voltage light simply means the airplane's bus voltage is below 25 volts. It normally should be around 28. Door warn or door warning means that the aircraft's cabin door is not secured and the aircraft is not safe for flight. Left and right alternator out means that either alternator is not producing power and not charging the battery. And if both of those come on at the same time, chances are you'll see the low voltage light come on after. Cabin altitude indicates the aircraft's cabin has exceeded 10,000 feet. Hyd press or hydraulic pressure means the hydraulic system is pressurized, and with this airplane, that will come on when the landing gear is raised or lowered. If there is insufficient hydraulic flow with the RPMs above 1,000, the left or right hydraulic flow lights will illuminate. Hydraulic systems may operate, but may operate slower than normal with those lights illuminated. If the left or right fuel low annunciator comes on, that indicates there's approximately 60 pounds of fuel in the associated tank. That is not a lot of fuel. 100 low lead weighs 6 pounds per gallon, so that is only 10 gallons of fuel. Annunciators marked spare are reserved for optional equipment. The green air conditioning hydraulic pressure light simply means the air conditioner compressor is in operation. Heater overheat, that means the heater is on, it got too hot, and it shut off by itself, and you cannot turn it back on until it's reset. If flying in conditions where icing could occur, the windshield heat can be turned on, and when that happens, the green windshield annunciator will illuminate. And chances are, if you've encountered that much icing, you're also going to see the surface de-ice light come on. That will come on when the tail de-ice boots are activated and have reached full inflation pressure. So that is really just a pressure switch. And finally, thank goodness, because I know annunciators are kind of boring, the last item is courtesy light. And the courtesy light will turn on the cockpit floodlights and the main cabin entry light. When sitting inside the airplane, the courtesy light can be turned on with this switch here. You can barely see the light come on, but also the white annunciator light illuminates. And this white switch back by the entry door can also turn on the same lights. And the light can be seen if we look up above the door. But if that light is turned on in the back, it cannot be turned off from the cockpit. It has to be turned off from the back. The electrical system consists of an alternator on each engine, each producing 28 volts of power, along with a 24-volt battery. Each alternator provides electrical power for the aircraft systems, as well as electricity to keep the battery charged. A volt ammeter like the one shown here can be used to test the health of the alternators and the electrical system of the aircraft. To test an alternator, turn one alternator off. In this case, we're going to turn off the left alternator. The amps go to 0.
And now we want to take the selector and move it to the operating alternator.
And now we can see the amp load increase to approximately 80 amps, and the right alternator has taken up all the load. And switching the left alternator back on, the amperage will go to about half, indicating that the alternators are sharing the load.
This test can be done for the right alternator, but I'm not going to show that because it's identical to the left alternator test.
The battery switch controls power to the battery bus. If both alternators fail and the battery bus voltage gets below 25 volts, we'll get a red annunciator message as we talked about earlier. But also if the battery switch itself is turned off, that will also create a situation where there's less than 25 volts, also triggering that red annunciator message, as you can see there. Moving up from the electrical section, we have auxiliary fuel pumps. These are 3-position switches, high, off, and low. The checklist will indicate which position to use. These fuel pumps, which differ from the engine-driven fuel pump, can provide up to 5.5 psi for vapor clearing and purging. The low position is normally used after start and during climb up to cruise, and the auxiliary fuel pump would be placed in the high position in the event of an engine-driven fuel pump failure. If the engine is cold, more than likely, priming will be required. To prime the left engine, move this white switch to the left and to the right for the right engine. When the left or right primer is selected, the auxiliary fuel pump is energized, and the system will start spraying fuel into the intake ports. Pushing the start button closes the start contactor and allows the starter to be powered by the battery to start the engine. And provided the Magneto switches up here are turned on, the engine should start. There are 4 Magneto switches, 2 for the left engine and 2 for the right engine. To learn more about magnetos and aircraft ignition systems, I'll put a link to a video I did in the description. Moving down to the system switches, the white switches are all systems as far as lighting, air conditioning, and heating. The green switches are all anti and de-ice switches. Starting at the top with the anti-collision switch, that's nothing more than strobe lights on each winglet, as seen here on both sides of the aircraft. The nav switch turns on the navigation lights, which should be used at nighttime, and that's simply just a red light on the left wing, a green light on the right wing, and a white light on the tail. That's standard among all airplanes, or at least all airplanes with an electrical system that are certified to fly at night. The taxi switch turns the light on attached to the nose gear. This will rotate left and right as the aircraft is turned to the left or right. Landing lights are on a 3-position switch, on, off, and retract. When the switch is on, the light can be seen like this. Switch is moved to the off position, the light turns off, but the light is still extended. When the retract position is selected, the light is still off, and the light will retract into the wing. If icing conditions are encountered, the surface de-ice switch can be activated, and when that is done, the tail de-ice boots will inflate for 6 seconds, followed by the wing de-ice boots inflating for an additional 6 seconds, completing the 12-second de-ice boot cycle. And these are de-ice boots. If you've ever wondered the difference between de-ice and anti-ice, de-ice gets rid of ice, anti-ice prevents it. And to help see ice, there's a de-ice light that just turns the light on and illuminates the leading edge of the wing where the ice would accumulate. Prop anti-ice is used to prevent the formation of ice accumulating on the propeller. Near the center of the propeller, heading out towards the middle of the blade, you can see these black areas where the heated section exists. And notice the heated section does not go all the way out to the tip. The reason for that, centrifugal force is so high that ice should not be able to stick to the propeller in those areas. In the real world, my experience with these on Cessna 404 and Cessna 421s, they do work well, but also when in icing conditions, ice will fling off the side of the propeller and smack the side of the airplane, so you constantly hear little chunks of ice slamming into the side of the airplane. And it does damage paint. Normally there's a little pad there that will help protect the paint and the actual metal of the aircraft. When prop heat is turned on, and if this needle is outside of the green arc, the blades may not be heating evenly, which would likely lead to vibration. Anti-ice electric is actually windshield heat, and only the pilot side window is heated. It is a glass window with heating elements inside of it. The right side is plastic. The low position should be selected anytime entering visible moisture below 40 degrees Fahrenheit, and the high position if the outside air temperature is below 10 degrees Fahrenheit or negative 12 Celsius. And if you're wondering what visible moisture is, it's any precipitation or visibility less than 1 mile. For ventilation, there's a 2-speed cabin fan, high and low. This does not activate heating or cooling, but if the cabin heat switch is activated, the cabin fan automatically goes to the low speed. The heater is a gasoline combustion heater which uses the aircraft's fuel and is controlled with this knob here. When cabin heat is used, at least one of these controls, defrost, aft, or forward, need to be pulled out. And if you can't remember that, there's a placard right here. The cabin heat knob is rotated all the way to the right, the film is fast forwarded, and you can see the temperature increasing rapidly. There is also another way to put heat inside the airplane's cabin, and that is done with these knobs labeled left hand and right hand warm, which are left and right hand heat exchanger control knobs. If the knobs are rotated all the way to the left or the cold position, it opens up this valve on the wing root. If the knob is rotated to the right, to the warm position, the valve is then closed like this. And a schematic like this one will help us figure out exactly what's going on. There's one of these valves on both sides of the airplane. The knob we're moving controls the valve that is here. Warm air coming into the cabin goes through this heat exchanger. When the valve is fully opened, that allows more air to flow through the heat exchanger and cool the incoming hot air more. Looking at that same valve on the left wing, if the valve is closed, this would be the warm position, the incoming air going into the cabin would not be cooled at all. And if you're wondering where that warm air comes from, this schematic will tell us. As stated earlier in the video, the turbocharger increases the performance of the airplane, but the turbocharger also provides other services or functions. One of those is cabin pressurization. Looking at this schematic, you can see the turbocharger. There's a turbine side and a compressor side. Coming off of the compressor side is a line right here that says to cabin pressurization. As air is compressed, the air temperature increases. That is where the hot air is coming from. There's a lot more information on this schematic, which we will come back to later when we get into the climb section. Stall and vent heat will heat the stall vane electrically and provide a stall warning in icing conditions. Pitot heat simply provides electrical current to heat the pitot tubes, and the pitot tubes provide an input for the airspeed indicator. If pitot heat wasn't there and that pitot tubes froze over, the airspeed would not be accurate. And last of all on this panel, the avionics bus. This switch allows multiple pieces of avionics to be turned off and on at the same time. This switch would be in the off position prior to engine start. After the engines are started and the alternators are online, then the avionics switch would be selected to the on position. This is also a way to protect the avionics during engine starting. Another option this airplane has is an air conditioner. The air conditioner also has 2 blowers. Those can be used for ventilation in the circulate position, which is selected right there. And in this position, the air conditioner is still not turned on. When the cool position is selected, the air conditioner is actually on, and it can also be backed up by looking at the annunciator that says air conditioner hydraulic. Temperature is controlled with this knob here, and then blower speed can be selected low or high with this switch here. And looking up at the iPad on the left and speeding up the time a little bit, you can see the temperature starting to decrease. Since we're looking at the annunciator, let's look at one more of those red messages that doesn't really fit with any other system. And that message is door warn. That was the red annunciator on the top right. Anytime the main cabin door is unlatched, you get that red message. Moving on to the pressurization system, there's a switch labeled pressurize and depressurize. This airplane can be flown in either mode. When the aircraft is flown depressurized, the cabin rate and the airplane's rate of climb or descent are going to match one another, as well as the cabin altitude and the aircraft altitude. But if we select the pressurized position on the switch, the aircraft will begin to pressurize. So now air is being pumped into the airplane, and the air being expelled out of the airplane is being limited so that the pressure inside the airplane can increase. As an airplane climbs, the pressure outside the airplane decreases. As the airplane descends, the pressure outside the airplane increases. Looking at the cabin climb, we're descending at 1,000 feet per minute, so the aircraft is decreasing in altitude on the inside of the airplane, increasing the pressure. Right now the airplane is at 4,000 feet, but the cabin altitude over here is around 2,000 feet and decreasing. So in the example I just did, I started out in the depressurized mode and then turned the pressurization system on. And now the pressurization system has to catch up to where it would have been. As the aircraft climbs through 8,000 feet, you can see the aircraft cabin altitude approaching sea level. But also, as it approaches sea level, the differential, the small needle, is starting to increase. I've also selected cruise altitude plus 500 feet in the pressurization controller. And now looking at the cabin altitude, you can see that the airplane is at sea level and the maximum differential has been reached. So now the airplane can't descend anymore internally because the pressure will become too great. And if you're wondering what differential pressure is, it's just the difference in air pressure between inside and outside the airplane. The pressurization system is no longer allowing the maximum differential to increase. And for that to happen, the cabin altitude has to raise up some to decrease that pressure. The cabin rate is showing a 500 foot per minute descent. And in reality, that should be a slight increase. That should show a climb because the cabin is climbing. If the cabin rate of climb needs to be increased or decreased manually, that would be done with the cabin rate knob here. When setting pressurization, cruise altitude plus 500 feet would go on the inner scale, landing field elevation would go on the outer scale plus 500 feet. And looking closer at the pressurization instruments, you can see the cabin altitude is at 9,000 feet, the differential is at 5 psi. And for landing, the differential should be at 0. There's also an emergency oxygen pull knob. So if the aircraft cabin altitude exceeded 10,000 feet, an annunciator would come on, that knob would be pulled, and an oxygen mask would be placed on for normal breathing. While we're on the subject of high altitude, let's take a look at that manifold pressure gauge. Normally during climb, the manifold pressure would be reduced to around 35 inches just inside the green arc. I've selected maximum power, and look at what the manifold pressure is doing. It's decreasing. The engines are turbocharged, but as the airplane climbs, it's losing approximately 1 inch of manifold pressure per 1,000 feet of altitude increase. During a normal climb, if 35 inches is set, it'll just stay there up to a certain altitude. This airplane has an automatic wastegate, and let's take a look at what that is with this schematic. To simplify how this works, exhaust gases go through here and spin the turbine here. The more exhaust, the faster the turbine can spin. The wastegate over here limits the amount of air going to the turbine. For example, at low altitudes, the engine can make quite a bit of power. Not as much boost creation is needed, so the wastegate can go to the open position and expel more exhaust gas to make the turbine not spin as fast because it's not needed to spin as fast. At high altitudes, the engine needs to create more boost. So in order to do that, more exhaust air goes through to the turbine. That wastegate closes all the way, so all the exhaust air is going to go through, hit the turbine, and spin the compressor faster, providing more air to the engine. When the wastegate is fully closed, additional boost cannot be created from that point. So as the aircraft climbs, the maximum manifold pressure will no longer be able to be sustained. And that's why you see the manifold pressure drop at high altitudes. When the turbocharger can't produce any more power and the engine starts to lose power, that point is what is known as critical altitude. And in this airplane, that altitude is somewhere in the vicinity of 20,000 feet. There are a few limitations for the turbocharger. One of those is right here on this placard, which gives the maximum manifold pressure based off of altitude. And while we're still on high altitude operations and just finishing pressurization, what if we wanted to depressurize the airplane? One way to do that is to push the switch to the depressurized position. The other way is the pressurization air pull knobs. They say pressurization air pull to dump. That is stopping the inflow of air coming off the turbochargers at the wing root. And if this position were selected, a descent would need to be started because the aircraft would slowly start to depressurize. But for normal operations, both of these knobs would be pushed in all the way. And an additional way to depressurize the cabin if needed for smoke removal is ram dump. And if you're curious what those switches and knobs are connected to, here's the schematic, and all the items we just dealt with are right here. If you're flying a carbureted airplane and get carburetor ice, simply turn on the carburetor heat. But a fuel-injected airplane doesn't have that. It has an alternate air source. Instead of getting cold, filtered air to the engine, pulling the alternate air source will provide warm, unfiltered air to the engine. Use of alternate air should be kept to a minimum, and it can also reduce engine power slightly. The fuel system consists of 2 tanks, one in each wing, for a grand total of 206 gallons. There are also 2 annunciator messages associated with the fuel system, and they are the left fuel low and right fuel low. As talked about earlier, these annunciator messages come on when there's approximately 10 gallons of fuel left in each wing. Moving on to one of my favorite parts of this airplane, the Hoskins fuel totalizer. This is actually quite easy to set. It looks more intimidating than it really is. To set it, let's do some math. We've added fuel. The fuel totalizer has 115 gallons set on it. Fuel was added. There's 80 gallons per wing for a total of 160 gallons. 160 minus 115 is the number that we need to enter into the fuel computer. Here we have the choice to fill up. If we want to fill up, we just go down and hit the enter button to verify it. We don't want to do that. We want to add 45 gallons. So we're going to press the
Function again.
and one more time. Press it till we see the 0 in the column we want. Enter 4.
Press the function button again.
And go to 5. That's adding 45 gallons to the current fuel load. We see the verify light. Press enter. We now have 160 gallons. And now the function button can be pressed again to change menus and see, for example, pounds remaining versus gallons and other options as well. But what happens if we accidentally press the fill up button or we add too much fuel? How do we reset the fuel computer? There is an easy fix for that, but real quick, that low fuel light that's flashing on the fuel computer, that means at the current power setting, there's less than 1 hour of fuel remaining. Now, to reset that computer, turn the battery switch to off, go back up to the fuel computer. Down in the bottom right corner, the other button is the test button. Press and hold that, and then turn the battery switch back on. And once that's done, the fuel computer is reset. It's essentially at its home screen that you normally see on the first power up. And here it was just indicating 0 gallons. Now all you need to do is read the fuel gauge and put in the total number of gallons. In this case, still 160 gallons. So if you don't want to do the math, an easy way to do it is put the battery switch to the off position, hold down that test button, and then just enter the total fuel amount. Another thing that could happen with the fuel system is to have a fuel imbalance. The airplane could have been misfueled. Maybe you're running on one engine for a while. The engine was restarted, and now you're left with this situation. How do we fix that? With this, fuel crossfeed. The right tank was heavier, so you can see we took the left engine. Now we're feeding the left engine from the right tank. The left main tank is staying where it was when the selector was changed, and the right main tank is decreasing. So now both engines are being fed from the right tank. Now let's say for some reason we're crossfeeding. We have to make a gear up landing and we need to stop the crossfeed. The way to do that is the emergency crossfeed shutoff lever, that red lever between the seats. In this situation, the left engine was being fed from the right fuel tank. When that lever's pulled up, the left engine is no longer being fed from the right main and the left engine has quit. But let's say both of the engines are working again and now we need to put the gear down. The landing gear is electrically controlled and hydraulically actuated. It can be extended and raised up to 177 knots indicated airspeed. There is a gear warning horn if the throttle is brought back to approximately 15 inches of manifold pressure. With the gear up, you will hear a buzzer like this. That lovely buzzer will continue until the throttle is increased or the landing gear is in the down and lock position. When the landing gear is selected down, the gear unlocked light illuminates and also the hide press annunciator illuminates. When gear retraction occurs, the red gear unlocked light will come on and also the hide press light will illuminate on the annunciator panel. An extension normally takes about 4.5 seconds. Also, extending the flaps beyond 15 degrees and pressing the press to test over here should also trigger the gear warning horn. I haven't tried it to see if that works, but it would be awesome if it did. Let me know in the comments below. The landing gear does have a backup extension system. If for some reason the hydraulic system fails, there is a backup method for blowing the gear down. And that would be done with the nitrogen bottle in the nose. The gauge we're looking at shows how much nitrogen is in that bottle. The airplane is not programmed yet to have a hydraulic failure, so the only way to give myself a hydraulic failure for this example is to shut down both engines and feather both propellers so the engine-driven hydraulic pumps can't work. And when gear down is selected and nothing happens, you would pull the emergency gear control T-handle. This releases that nitrogen charge into the gear system and pushes the gear down. In reality, that would not be done without the use of a checklist. You can see and probably hear the gear coming down incrementally. Thankfully, in my 20+ year career as a professional pilot, I've never had to blow the gear down. In nearly 20 years of flying citations, it's a very similar system. When that handle's pulled, the gear usually comes down in one fell swoop. And no, that's not a technical term. When the T-handle's pulled, you don't always get a 3 green indication. Sometimes the airplane has to be banked left and right and yawed left and right. And this yawing is extremely excessive. This is the same shot. I just went back to the inside view. You can still see both engines are shut down, but there's also a down 3 green indication. And that demonstration worked as advertised. And with both engines turned off, even sitting on the ground, that brings us to the next question. The flaps. If both engines are shut down, there's no hydraulic power, will the flaps work? And the answer is yes. The flaps are electrically driven, not hydraulic. Some 400 series airplanes, the flaps are hydraulic. This one, they are electric. The flaps have 4 positions, 0, 15, 30, and 45 degrees. The first notch of flaps, which is 15 degrees, can be added at speeds up to 171 knots. But flaps beyond 15 degrees cannot be added until the white arc, which starts at 140 knots indicated airspeed.
There's another type of flap on this airplane, the cowl flaps. And their main purpose is to help cool the engine. You can see the cowl flap open on the bottom of the left engine. There it is from the back. You can see how it opens up and lets more air come through the engine. And they would normally be open when the aircraft is at low airspeed and high power settings, such as in a climb. But even during cruise, if the cylinder head temperature starts to get too high, the cowl flaps can be opened to lower the cylinder head temperature.
And last of all, the very last system I'm going to cover in this video is interior lighting, specifically cockpit lighting. Obviously in the real airplane you can't push that screw and make the throttles, mixtures, and props disappear, but in this one you can, to get better access to the rheostats to control each section of lighting. You can push the day-night switch over on the left to activate the lights, and then move each rheostat to control the lighting for each area. And last of all, I want to see if anybody can tell me what that antenna is. I know some people will know, but that type of antenna is seen on a lot of different airplanes, but it's never really talked about. But it's also very common. Comment below and tell me the purpose of that fin-shaped antenna. This video is made to cover the basics of every knob and switch that can be selected from inside the cockpit. There's obviously a lot more information. The information given was very brief. Autopilots were not covered because I wanted this video to cover just the aircraft systems of the Cessna 414. I did do a live stream of the 414 where the autopilot's used and a lot of normal checklists are used. I will post that in the description and also in a link up here at the top of the screen. As always, thanks for watching, and if you watched the whole video straight through, I appreciate the time you took to do so. This is one of the best general aviation aircraft on Microsoft Flight Simulator. FlySimWare is constantly doing improvements. They even want to do improvements such as making the circuit breakers actually work. And that being said, this is going to be an even better airplane in the future.